Hi, everybody, and welcome back to chemistry. I'm going to give a go at recording this lecture, and hope you guys are doing well. This is a pretty low-tech way of doing this, so sorry if it is shaky. Just a reminder, when we left you, we had gone over some of the beginnings of this unit. We're talking about different states of matter, and I'm looking at my notes here. These notes are available on my MCPS, and we have already gone over all of these, so kinetic theory, talking about manometers. There's my favorite, sphygmomanometer right there. And that's how you measure pressure. All right. And we talked a little bit about those traditional manometers there. Remember, you are responsible for knowing the conversions of the different pressure units. Okay. And you had some practice on that before we left. All right, kinetic energy, which brings us to talking about temperature, remember? And that we're going to be soon doing calculations in Kelvin, so making sure that you can convert from Celsius to Kelvin. All right, so now starting with some new stuff. As I mentioned before, we're going to be spending a lot of time on gases later, but now we just want to talk a little bit about liquids. Liquids have a set volume, all right, but are going to take the shape of their container, and you guys know that from all the times you dealt with liquids. All right, the intermolecular forces in liquids are much stronger than those in gases, and that's why they are staying together, all right? Some things that are going to happen to liquids that we're going to talk about are what are known as vaporization, and vaporization is anytime you convert a liquid to a gas. Okay. The difference in the word gas and vapor. Gas is typically used for something that is a gas at room temperature, whereas vapor is used for something that is either a solid or a liquid at room temperature, but then we do something to change it to a gas. We'll really pretty much be using them interchangeably, but I just wanted to let you know the difference. All right, evaporation is a type of vaporization, but the important thing to remember with evaporation is that it is only occurring on the surface of the liquid. All right, so moving on, we're going to talk about something that is called vapor pressure, if I can get my computer to move. And I'm not sure why. There we go. All right. Okay, so if you look right there on the left, we have a container of liquid that's in a closed container, and we're just showing you the closed container by putting the cap on that flask. Well, the liquid at the surface is going to evaporate. Some of it does. Liquids at any temperature evaporate a little bit. They're going to hit the sides of the container. Remember, when gases hit the sides of the container, they cause pressure. All right. And eventually what's going to happen is some of those particles that hit the side of the container are actually going to condense and turn back into a liquid. After a while, we're going to get an equilibrium. Remember, equilibrium is where two opposing processes end up going at the same rate. All right. Ooh, right there, rate. Boom. Okay, good stuff. All right. And again, trying to scroll down. That's better. All right. Right here, this graph is called a vapor pressure curve. Okay. If you notice, you have temperature on the x-axis and you have pressure, this time in kilopascals, make sure you're always checking those units, on the y-axis. Okay. For this particular liquid, all along this line, that is your vapor pressure. What's important about this red line here is it's a little bit above 100 kilopascals, and we know that 101.3 kilopascals is standard pressure. When the vapor pressure of your liquid is the same as atmospheric pressure, all right, which is typically right around standard pressure for us, then you get what is known as boiling. Okay, so... All right, so before we talk more about boiling, let's just look at this. What will the water vapor pressure be at 60? So all you do is you go to 60 degrees, okay? You go up to see where the line hits, and then you go over and see what that pressure is. And obviously we're just estimating, and it's about 25 kilopascals. So as I was mentioning before, when a liquid is heated to a temperature at which particles throughout the liquid have enough kinetic energy to vaporize, we say that the liquid boils. And you guys know from watching boiling water, when water boils, you see bubbles. And that is because it is turning into a gas all throughout the liquid. And that's what's causing the bubbles, is you're actually getting that vapor even from the bottom of the container. Our normal boiling point is the temperature at which a liquid boils at standard atmospheric pressure. So when we say that the boiling point of water is 100 degrees Celsius, that is assuming you are at standard pressure, which again, as I mentioned before we left, we live at sea level. So typically on a nice sunny day, that is our pressure. All right, so here's a vapor pressure curve that has, that has 4 different liquids on it. And by looking at this, and I'll go in a little bit closer, again, still temperature on the x-axis and vapor pressure on the y-axis. And we can see our 3 different liquids. And you guys should have this graph. You can look in the documents, or it should be in your notes. You can do all of the same type of things. I could ask you questions about what will the vapor pressure be at a certain temperature? What would the normal boiling point be for all of these? And then we can even extend and talk about kind of the strength of the intermolecular forces between them. All right, because the higher your boiling point is, it means it takes more energy to turn that liquid into a gas. So what that means is you have stronger intermolecular forces. So looking at this, ethanoic acid, all right, has the highest normal boiling point. It is going to have the strongest intermolecular forces, whereas propanone, okay, which is over here, is going to have your weakest intermolecular forces. So some fun stuff we can do with that graph. All right. Okay, so at this point, I'm going to continue with the video, but at this point, if you want to stop and do the practice sheet on vapor pressure curves, that would be a great idea. All right, and then you can always come back. We're at about 6 minutes and 30 seconds. Come back for the remaining lecture. All right, so let's talk about solids. Solids have a fixed volume and shape. All right, they have a very orderly, the molecules are very orderly arranged. The molecules are the atoms. Particles are still moving. Remember, kinetic theory tells us that particles are always moving, but we say that that movement is really a vibration around a fixed point, which means they're not really moving a whole lot. If you guys decide to go on and take AP, you will learn about all the different, not all the different, but several different crystal lattice structures, which are the geometric shapes that these solids form. All right. But we are going to focus on some changes of state now. Some that we already should be familiar with: melting and freezing. All right, remember, melting is going from a solid to a liquid, freezing from a liquid to a solid. Vaporizing and condensing: vaporizing, liquid to gas; condensing, gas to liquid. And then 2 that you might not be too familiar with, one is sublimation. That's when you go directly from a solid to a gas and you skip that liquid phase. A substance that goes through sublimation is dry ice. Okay, so which is carbon dioxide. If you guys have ever had dry ice or used it for anything, you know that, it's very, very cold when you buy it. And then when you take it out, it just immediately gives you that fog. Well, it's the gas that it's producing. It does not go into the liquid state at all. The opposite of sublimation is deposition, and that's where you're going directly from a gas to a solid. All of these phase changes can be seen in this graph right here, which is called a phase diagram. Phase diagrams are fun when you see them online or on color copies of them. They typically have 3 different colors to show you the 3 different states of matter. All right, even on a black and white copy, your solid's always going to be over to the far left. Your gases will always be as far right as you can get. And then the liquid will be in the middle. Okay, all along the solid liquid line here, you have melting and freezing going on. All along the liquid and gas line, you have vaporization and condensation. And then along the solid gas line, you have your sublimation and your deposition. Okay. Right there in the center, you will see what is known, well, it's not really the center, but you see what I mean. It is the triple point. And at that point, you actually have all 3 states happening at the same time. At that pressure and temperature, you can get all 3 states. Feel free just to Google the triple point of water, and you can see some videos in there of it. It really just looks kind of like bubbly, foggy water, foggy ice water, but still pretty cool stuff that's happening. All right, so again, the triple point is the temperature and pressure where all 3 states exist. Another point on the graph that is interesting is what's known as the critical point, the temperature and pressure where the phase boundaries cease to exist. And really, we're talking about the critical point up here. You get to a point that no matter what you do with the pressure, all right, it's just too hot and you really can't tell the difference between a liquid and a gas. And that's really what's going on with that critical point there. All right, so let's just take a look at a couple other phase diagrams. There's one that's not quite as pretty colors, but again, you see your three different areas. You see your triple point there. All right, again, here we go, a little bit prettier one. You can get different shapes. If you notice, this one here is for carbon dioxide. So when we're at kind of our normal conditions of pressure, which now are in atmospheres, at one atmosphere, which is standard, you can see at cold temperatures, it's a solid. And then as we increase that temperature, we go directly into vapor. And that is how carbon dioxide goes through sublimation. All right, it's skipping this little liquid area here altogether. Okay. All right, guys, well, that's the end of your notes. At this point, what you should be doing is there is a practice sheet for your phase diagrams that you can work on. The answer keys are there for both the phase diagram practice sheet and the vapor pressure. I hope you enjoyed this 11-minute lecture, and I hope you guys are all doing well. All right, we'll be in touch soon.